Hi, welcome to another lecture on Calculus 2. Today we are going to continue our conversation about trig substitutions. I'm going to explain these three integration problems. We mentioned them at the beginning of the previous lecture. So we had these same three formulas here, and I want to explain how by using these trig substitution we can arrive at the answer in each case. So Uh, to do these, we need the trig substitutions themselves, and then we are going to require three problems we had done before. Integral of cosine square, we had done that a few lectures ago. So we had the integral of cosine squared using some basic trig identities, and then integral of secant. This is one of the basic integrals in calculus 1, you see. So is this one. We are going to require that, and integral of secant cube was the most complicated of these, and we had seen that in the prior lecture under the topic of self-referral cases. So we had exponential and secant, both of them covered in that case. So if you want to go back to refresh your memory, that's what you need to go back to. But now let's go ahead and see how we can derive these three formulas. The first one is the easiest. Let's go ahead and do that. So integral of a squared minus x squared. Let me rewrite that. Integral of, we have a squared minus x squared dx, of course. And the picture that goes with this, just to help you memorize perhaps, various arrangements are possible, but just to use a standard arrangement, if the one of the legs is a, that's going to be taken as the horizontal one. If one of the legs is x, and then the x is going to be taken as the vertical one, and then the radical is going to be always the third leg that you are looking at. Theta is always the same angle in this arrangement. So let's go ahead and reproduce our picture there. So a has to be, of course, the hypotenuse. If x is one of the legs, it's going to be the vertical one, and the angle theta is going to be this. We could have taken x as this one as well. It's just a plus or minus sign going to come in. So here in this case, x, the opposite of that is of course hypotenuse times sine of the angle. For substitution, we need the differential, so that's going to be a cosine theta d theta, and then the third side, of course, that radical, we are after a squared minus x squared in radical. So what we have is a squared minus x squared. Well, that is of course going to be a cosine theta. Now we can go ahead and derive some other quantities out of these things. For example, x over a. X over a is going to be sine of theta, and therefore sine inverse of this is just going to be theta. Okay, let's go ahead and do the substitution. Let's see what happens. Integral of this radical, we said, is going to be just a cosine theta. Dx is again a cosine theta d theta, and we are almost done because this is a times a is a squared. Integral of cosine square of theta d theta. And then you remember this is exactly what we did a few lectures ago. You have to go through a few identities. So this is a squared. Cosine squared, we can, for example, do it by double angle formula. So we say 1 plus cosine 2 theta over 2 d theta. So that's going to be a squared antiderivative of 1/2 theta over 2. Antiderivative of cosine 2 theta is going to be sine of 2 theta divided by 2, and I have another factor of 2, so that makes it a 4, and then throw in a constant. So I'll have a squared, this is theta over 2. Instead of sine of 2 theta, I can write this is another trig identity, 2 sine theta cosine theta from your trig class. So 2 and 4 is going to simplify to a half. I can take that half, put it outside to clean up. So that's going to be just theta, and then we're going to put half outside. Then I have sine of theta, cosine of theta, and a constant. So of course now I go ahead and do the back substitution. So theta was sine inverse of x over a. Sine theta, let me perhaps write it here. Sine theta is of course x over a, and I need cosine theta. Let me write it here. Cosine theta is going to be this radical over a. So we have done this thing before, so I'm going to be a little bit faster. So sine theta over a is x over a. Cosine theta is radical a squared minus x squared, that one also over a, and a constant. So if you multiply through, of course I'm gonna let's leave a half out, and then I'll have a squared sine inverse of x over a, and this a squared, it cancel the a's down here, so I'll have x radical a squared minus x squared, and then a constant. So that was straightforward by remembering our trig identities, and then we are done. Next up, let's go ahead, take a look at second one. You see what a huge difference it makes if x is first or x is second. They look pretty similar to each other, just off by minus, but you see instead of sine inverse we are going to have logarithm, and so on. So we are done with the first one. Of course, you notice we have derived that formula. It's written in sine inverse is first, but otherwise all the same thing. So let's go ahead and do radical. Now I have x squared then minus a squared dx. So in this case we said well, of course x has to be our hypotenuse, and then you have a choice of a here or here. To keep it simple, we take it the horizontal one and the angle theta, and then of course the third side would be the radical we are interested in. So x is of course a secant of theta, or you can say cosine of theta is a over x, or secant of theta is x over a, and therefore when you multiply by a you'll have x is equal to a secant of theta. Then we need our differential as well, so it's going to be a secant of theta tangent of theta, because that's the derivative of secant, then d theta, and then I need my radical x squared minus a squared. That's of course going to be the ratio of this to that is tangent of theta, so this is a tangent of theta. In reverse, if you want to consider it, secant of theta is going to be ratio of hypotenuse to adjacent, and then we of course need the tangent of theta. In our back substitutions is going to tangent of theta. Tangent of theta is opposite to adjacent, so let's record that for future use. So these are the elements of the substitution and back substitution. Now I come back here, I have that expression is a tangent that's the radical. Dx is this a secant of theta tangent of theta d theta. Now let's combine it. A and A is an a squared, comes outside. Then I have tangent squared and then times secant. Well, what to do now? You remember basic trig identity that 1 plus tan squared is secant squared. So if you want to convert to all secants, this can be written as secant square of theta minus 1 times secant of theta d theta. So that becomes a squared. This is secant cube of theta minus secant of theta, all of that d theta. Okay, now you see why we needed those two formulas. Integral of secant cube, that's the one we had done a couple of lectures ago and was one of the trickier ones. And secant of theta was from calculus 1, and that is also quite interesting in its own right. So I need these two. What do I have over there? I have difference of secant cubed and secant. So if you take this and subtract that from it, well, that logarithm subtracting from a half of a logarithm is going to become minus 1/2 of the logarithm, and we just allocate one constant. So here, rather quickly, what we have is a squared times, so we had secant of theta tangent of theta, we had a factor of 1/2, so let me just put my 1/2 outside. And so that when we do the subtraction, what we get is minus logarithm of secant of theta plus tangent of theta, and then we throw in one constant and then replace a squared over 2. Secant is x over a, tangent is this other one, minus logarithm of just sum of these two, x over a, and then I have the other one, radical x squared minus a squared over a, plus a constant. So when I multiply through, of course a squared cancels these, so we'll have 1/2 of x radical x squared minus a squared, and then the other one is minus a squared over 2 of logarithm of. So I put an a in the denominator and take a common denominator. Okay, so logarithm of a ratio, we have seen this before, a logarithm of numerator minus logarithm of denominator. Logarithm of denominator is a constant, we can absorb it in this constant, so we can clean it up and write it as 1/2 of x radical x squared minus a squared, and then I have a squared over 2 logarithm of, just going to be the numerator. So what happened to the denominator? We said use the rule of log, that just becomes a logarithm of a. Since a is a constant, that's also a constant, and you combine your constants into a single one, and then you're all done. That is the second of these we wanted to show, and we see that that comes out just as that didn't come out looking nice. Let me erase it. My computer decided not to cooperate with me. Let's see. In the third lecture, the third formula we have very similar to the last one, radical x squared plus a squared. We're going to use this formula, so radical let's see if I have better luck this time, hopefully. So the last of these three is radical x squared, radical x squared plus a squared. This is very similar to what we just did. So if x is a leg, it's going to be this one. If a is a leg, it's going to be this one, and the radical will be the third one. Our angle is always this one, the angle theta. So in this picture, we will have x is equal to, of course, a tangent of theta, and therefore dx going to be a secant square of theta, and then the radical is of course going to be a secant theta. So when we do substitution, the radical immediately is a secant, and dx is a secant cube, excuse me, secant, of course, secant square, and then when you multiply it, well, a and a comes out, and then I have the secant cube now. So this is back to that very interesting integral we just saw a second ago, integral of secant cube. So that's why we listed here. We have the answer straight out from our lecture a couple of weeks ago. So let's just write that. And that is a squared. A factor of 1/2 comes here. Secant of theta tangent of theta plus logarithm of secant of theta plus tangent of theta, and then a constant. So a squared times let's write this thing, secant of theta. What is that? Is that radical x squared plus a squared over a. How about tangent of theta? Tangent of theta, well, that's going to be x over a. So when we say secant tangent is a product of these two, when I multiply by a squared, the a squared in the denominator is going to go away, and I'll have 1/2 of the product of these. Let's write the x first, so it looks nicer this way. X squared plus a squared. Now a squared over 1/2 times this, logarithm of secant, again just that integral, the radical, divided by a, and then a tangent x over a, and then we have some constant. Just as in the last problem, we can put the a's as a common denominator, and then logarithm of denominator has to be subtracted. Since it's a constant, we can merge it with this constant, and as a result I'll have 1/2 of x radical x squared plus a squared, and then a squared over 2 of logarithm of, customary write to small items first, x, the same as above, x squared plus a squared, and then some constant, you either rename it or just call it k. So that becomes the third formula. So these are the three basic formulas that show up in a variety of applications in physics and engineering, and we wanted to show that they can be done by the trig substitution and integrations that we had done before. Okay, so what you want to do is to write them in your table of integrals, If you have a chance to look at the end of your textbook, you will see a very long list of this type of expressions, perhaps close to 100 of them, of various integrals and how to approach each of them. Some of them quite a bit more challenging than the one we just did. Okay, until the next lecture, which is going to be on partial fractions. Good luck and God bless.